Hey, good morning, good afternoon, good evening, everybody. My name is Yann. I'm Associate Director in charge of machine learning for MCU, and I want to welcome you to a new live stream about machine learning here. I have two guests with me, Alex here on the studio.
Hi, Yann. Glad to be here today. I'm Alex Jagger, an applications engineer here at Microchip, and excited to show you some new solutions we have with Edge Impulse.
And talking about Edge Impulse, we also have on Skype Yann from Edge Impulse.
Hi, I'm Jan Jongboom. Thanks, Jan and Alex. Yeah, my name is Jan Jongboom. I'm the CTO and co-founder of Edge Impulse. I am straight out of Amsterdam, so really far away from Arizona where the studio is. And we founded Edge Impulse. Both me and my co-founder are former ARM engineers. We founded Edge Impulse for embedded developers to start building real production-grade machine learning solutions with sensor data. And very excited to talk about that and machine learning in general today.
Thanks, Yann. So before we dive into the subject, some housekeeping from Mike.
Yep, thank you, Jan. So we are live on LinkedIn, Facebook, and YouTube. So please share to your friends. We'd always like more people coming to see what we're offering. Also, if you want to ask a question, please ask it in the chat, and we will try and get it through to these guys out in the studio. And also, if we can't get to you, please email us at livestream@microchip.com. Also, today we do have a giveaway. So we have this board, which is the SAM D21 Machine Learning Evaluation Kit, and I believe we have probably 4 of these to give away.
Correct.
But to be eligible to win, you need to go and complete the survey at the end of this live stream. So, yep.
Thanks, Mike.
So back to you, Jan.
Thank you. So Yann, we are talking about machine learning, for some time, and the question is always, how can machine learning help me in developing better application or better project, better products?
Yeah, that's a good question. I kind of see it that every time you have a problem where you're looking at sensor data and you can't easily kind of find a pattern in that data yourself by looking at it in Excel or plotting graphs, and you can't distinguish kind of the formula that maps the inputs to the outputs. That's where machine learning really shines. It can map really complex inputs to output and kind of find that hidden formula for you. So as an example, let's say that you're building a system that needs to distinguish whether water is boiling. So you start out, you get a temperature sensor, you put it in water, and you kind of observe like when the water starts cooking. That's at 100 degrees Celsius. I don't know what is in Fahrenheit, 200 degrees Fahrenheit, something like that. So you write an application. You say, okay, well, if temperature is above 100 degrees, then water is boiling. Now you start observing that if you're mountain climbing and you're at 2 kilometers high and you test this again at 98 degrees, according to your algorithm, water should not be boiling, but it is. And we see that with sensor data, there's lots of potential variables where that can match. So the idea of machine learning is if you can't find the pattern yourself, you try it in Excel, you can't find the hidden correlation, you can give the inputs and the outputs to the ML algorithm, and it can find that hidden formula for you. So that's really great for stuff like detecting words or audible events, because there's infinite number of sounds that can play around you. For anything that deals with images, it's really hard if I give you an array of pixels that you tell me, oh, do I see a cat, a dog, or something completely different, or something broken on a factory line? And machine learning can help you find these uncover kind of these hidden correlations between things. So anything with messy, high-resolution sensor data is a perfect fit for machine learning.
So in time of, you're talking vibration, audio, images, so all type of sensor here?
Yeah, so vibration data, does a machine vibrate in a pattern that I've seen before, or does a machine oscillate differently than all the other machines in a factory? That is hard to uncover. Maybe you can do it for one machine, but every machine is like a different pattern, and finding this out automatically, it's great. As said, anything with audio is really hard. In essence, audio is a really simple signal. It's a waveform, and it's really relatively easy to say, okay, well, I want to be alerted when I hear sound above a certain threshold, or I hear a constant beep at 7,000 hertz. it's much harder to say, I want to get alerted when I hear a dog barking, or I want to get alerted when I hear glass breaking, because there's so many different ways of different sounds around this. And then last, yeah, anything with image data. But there's lots of stuff that we don't really do right now on embedded systems. LiDAR, for example, radar segments, kind of anything where we have high resolution messy sensor data, that fits very nicely here.
So based on what you just said, so do you see any market who can benefit more, or is just so broad that anybody can enjoy that?
Yeah, that is a hard question. Like, my feeling is that machine learning is so applicable to so many areas, because everywhere around us is data, and lots of this data is currently it's kind of thrown away even when sensors collect it. So typical industries where we see stuff happening early on is in predictive maintenance. So anywhere where you have really high value machines and you want to know whether those machines work properly or whether there's a chance of breaking. Naturally, because these are really high value use cases, that's where initial development goes. We see quite a bit in healthcare. So with COVID especially, there's kind of a big push internally to see, okay, can we detect when there's lots of people already wearing wearable devices all around. And these devices collect data all the time. So this is data like information about bloodstream, and from that you can derive heart rate variability, blood oxygen levels, as well as accelerometer data, so what is someone doing, and skin temperature. Now, what we see already from customers from us is, okay, can we actually use that data to do things around, for example, COVID onset detection? Can we know beforehand that a person is getting sick just based on the sensor data? Now, sensor data has always been thrown away, and it's data that you can't easily send to the cloud for analysis because, well, first of all, it's very personal information. I don't want to get like raw data from my bloodstream sitting somewhere in a cloud. And it's lots of data. Like just syncing data for 1 day over Bluetooth takes about 2 hours, and no one wants to sit next to that charger for 2 hours until the data is sent over. So kind of industrial use cases, consumer health, but yeah, we see lots of opportunities around asset tracking. Do I know what is happening to a package going around? And my feeling is that 10 years from now machine learning will be a tool in every embedded developer's toolbox that's being applied the moment that you see a use case for it. And that's why I think it makes it super exciting.
Yeah, because the trend is really to go to, I think you mentioned that a little bit, but is really to go to the edge, correct? Is not to send all the data to the cloud for many, many reasons that maybe you can explain here.
Yeah, I mean, if you look at kind of every device has constraints, right? Especially if you look at embedded devices. There's a reason why we stick an MCU in a product, and lots of these constraints. Kind of the biggest constraints I see is power constraints. So we have lots of devices with a battery. There's just no way that we can send raw waveforms of sensor data to a central location because then we burn through our power budget really quickly. We have cost reasons. So even if you have a Wi-Fi connection and you can send and your main's powered, there's a cost involved in actually sending that data to the cloud and processing it there. And there's lots of data in the real world. Swim.ai, a startup that we used to work with at ARM, they augmented all the streetlights in San Jose with sensors to analyze traffic. And just the amount of traffic coming from those traffic lights on a single day was more traffic than all of Twitter combined, and Twitter might be able to pay for all of the traffic, but a municipality is definitely not. Yeah. So you need to process it there. So yeah, costs, bandwidth, and power constraints are kind of the main reasons of pushing it to the edge.
So now we have to define what the edge is, because for Microchip it's an MCU, and we're convinced that it can work on an MCU. Some people are questioning that. How can we help them understanding that yes, an MCU is a good fit for machine learning?
Yeah, I mean, I think the most important thing to realize here is that machine learning is not a magic special little black box or something. It's not a magical thing that you put in your device and then it starts sensing the world. it's just mathematics underneath. And our sensors are already really good at doing mathematics. If you look at a 7051 Cortex-M4 device, it's capable of doing 40 million instructions. Simple instructions, but 40 million instructions a second, which is astonishing. So I realized that, one, it's just mathematics underneath. And second, we've been doing on-device intelligence for a long time already, which is called signal processing. And kind of the way that we approach it at Edge Impulse is say, well, first, we just do whatever we've done for the last 50 years. We build upon the common knowledge of the industry. So first is let's just look at the signal. What can we just extract from that signal first? So we do stuff like fast Fourier transforms over data. We look at the kind of time frequency domain for data, see what we can find from there. If we can pull up slide 1, we did so this is cool. Like already, so this is me saying 2 words. First is microchip. So you see nicely 3 syllables. So this is a spectrogram derived from an audio file. And then on the bottom, it's Edge Impulse. And that's 2 syllables with a little bit at the end. So you might look at that at the base waveform, and you might realize, okay, well, it's sort of impossible to distinguish between microchip and Edge Impulse from that. But then actually we do a whole bunch of fast Fourier transforms over this data and build a spectrogram, and here it's actually optimized for human speech. Then already I can distinguish between these 2 things very, very quickly. So this is data, no machine learning involved in the slide that you see here, but this is just the data from a keyword spotting data set, so raw audio data. We've put that through a Mel frequency Setzel coefficient feature extraction block, so a bunch of FFTs, and that's normalization. And then we plot that, we compress it down to 3 axes, and then we plot that into a graph. And already for 2 different words, here is yes and no, we can already start seeing the distinction between these 2 things. So what the machine learning algorithm needs to do after is just draw a line, and it's probably not a linear line, but just draw a line between these 2 things. So we feel that by combining signal processing, which we know that devices can do very well, combined with some machine learning to then better do thresholding and better segmentation, we can build really, really powerful things. And then in the end, it's just mathematics, and we have vector extensions on device that can do this stuff really efficiently. We've realized as kind of an embedded ML community that during training, when you try to find this magic formula, you need really high precision, but you can kind of tone that down when you run this on device. That way we can make this run really fast, really efficient. And yeah, that's what we are right now.
So it's a good fit for an MCU, and I think the screenshot we showed was you will see more on the from Alex's demo later during the show here, but it's all the tools that Edge Impulse is also giving the designers to make sure that the data they have are correct and can be used effectively.
Yeah. So I think we have an example of 2 pipelines actually with the numbers and how long that takes. So on slide 3.
Yep, here it is.
Yeah. So this is actually a normal vibration pipeline that we use for predictive maintenance, for example, on rotating machines. So how we approach that is we look at the signal. So we have sensor data coming in at, let's say, 1,000 hertz. What we want to do is run a fast Fourier transform over it, the same stuff as you do 5 years ago. And then we look at the power spectral density components of the signal, and we look at where the peaks in the signal are, and that's our DSP pipeline. And that is efficient. So this is on our Cortex-M4F. We can do that in about, let's say, 10 milliseconds with 5K of RAM, depending on your FFT length. Afterwards, we have features, the same features that you might previously have used to do some basic calculation on that signal. So the height of peaks on FFT length, power spectral density buckets, and that we can feed into a neural network. And because we already did lots of pre-processing, we've done lots of filtering beforehand to make sure that that is actually clean data, we can have a very small neural network to the end classification. So we can run this whole pipeline in 10 milliseconds with 6K of RAM. And that applies to higher resolution data as well. On the slide after here, you'll see an audio pipeline. So an audio pipeline has lots of information in the time frequency domain, so we need to do a lot of FFTs. So the inferencing time for that part is a bit longer, 300 milliseconds here. And afterwards, but that's stuff that we understand and the stuff that we can accelerate very nicely. And after that, we already have a clean data stream. Like if you remember the 2 keywords that we saw, you see like 2 halves earlier on. That is already, that is already after the DSP results. So we've already cleaned up the data with knowledge that we already have. And then finally, we can run a small neural network to do the final classification. So really nicely. My kind of gut feeling was always Cortex M0 Plus can do anything vibration data. What we're going to see in Alex's demo is exactly that. It's a real machine learning use case, an actual machine learning use case. I could see that in the product running on M0 Plus. Audio data can run on an M4 and up. And then for image data, you can do actual real image classification on live video feeds these days in a Cortex M7. And if you need more, you can go to an MPU.
Okay, so this is for the CPU side of it. The other question usually is also, I'm trying to integrate all my application. Machine learning is not just it's one piece of the puzzle that I'm trying to build here. And we saw some data on the slide that we can maybe show again on kind of the memory side that are needed for machine learning, because people think that they need hundreds of kilobytes of flash or RAM.
Yeah, so it's actually very little. Like in essence, so how I see this, like when you're training a machine learning model, when you have all these inputs and you have the output, yeah, that is a really, really inefficient process, because you start at kind of a random state. You say I have, I don't know, 4,000 parameters, a function with 4,000 parameters. They're all randomly initialized. Go find me the formula that best maps the inputs that I have, my raw sensor data or my DSP results, to these outputs. Very intensive process. We use GPUs in Edge Impulse, so if you train something in Edge Impulse, we'll give you access to a machine that does the training for you. But the final formula is just mathematics and something you can just write to ROM. So for our neural networks, we just literally write C++ code to a file, and you compile that file, and that's it. So there's nothing except for kind of the basic mathematical operations that you need there, which I think is super powerful. And if you start thinking about machine learning as that, just a different way of finding formulas, then you start realizing that it doesn't take a lot of RAM and doesn't take a lot of ROM. And the way that we design our SDKs is that we kind of turn your sensor into a predictive sensor. So we give you like how you buy a digital temperature sensor, digital thermometer. And you have a library that just talks I2C to the device, and it tells you what the temperature data is. Similarly, we give you a library. You just ask what is happening right now, and we'll tell you, oh, I hear glass breaking, or the machine is vibrating normally. Just a single call, and you write your application in the exact same way as you normally do.
Okay. So
and I think Alex has some numbers actually on the demo that you guys have been building.
Exactly that.
To do some verification on Microchip.
Yep. For my demo, using accelerometer and gyroscope data on the M0 Plus, it's using about 50K of flash for the full library, and that's the drivers for the sensor, as well as the full embedded inferencing SDK.
Okay, so it's pretty small, so it can be integrated easily in an MCU world if needed. So, okay, so now we say, okay, the CPU is good. It doesn't take too much memory, so you should be able to use it in your application. How do we help them? How do we help the designer now to move forward?
Yeah, I think the most important thing to realize here is that everything with machine learning really starts with data. And so you know that if you know that something is going to fit, great. But the use case that you have and that you're trying to apply machine learning for is completely different than what Alex is trying to do or what I'm trying to do here. So my kind of the first guess here is just verify that the problem that you're trying to solve is solvable by machine learning. So I think one of the cool things that we've done in the project now with Microchip that Alex will show in a little bit is we've made really nice tools in MPLab to actually collect data from real sensors. So real sensors that you have spread around. So as long as you have some data streaming into the MPLab data acquisition flow, we give you a nice way of pushing that data to the cloud and actually look at the data from a machine learning perspective. Like, does it have interesting components where we can read some data from? Then we will provide kind of the infrastructure in Edge Impulse to train that model. And with train, we mean slice your data up into common size length, do some basic manipulation, look at a signal processing pipeline, look at the machine learning pipeline, whether it's classic ML or neural networks, and finally verify it with real data flows. And the cool part there is, once again, you can use what we built with MPLab for that. So once you've trained the model, you just switch the flick in MPLab and say, now I want to test my device data. And without even flashing anything on your board, we'll now stream data from the device and then classify it with the model that we trained. And then finally, when you're happy, you click the C++ library, export in Edge Impulse, and what we'll give you is source code. It's source code to do your DSP operations, it's source code to do your neural networks, and it's source code to run your, for example, anomaly detection blocks. And the cool part here, and I think is the brilliant part of what we've been doing with Microchip is, it's source code, so it compiles on anything. So if you have whether you have a SAMD21 M0 or you have a SAMD51 M4F, this will just compile as is. And on the bit higher spec devices like a Cortex M4F or a Cortex M7, we can even use the vector extensions on your board, and we'll load that automatically in. So there's nothing for you to change. You just load the library and you compile to make that faster. So I think for Alex, we've managed to get compilation time down, or inferencing time down, from half a second to 150 milliseconds.
That's great.
Just thanks to the optimizations that we can load there, which I think is super powerful. So we have one great end-to-end flow that works on any Microchip IP in the tools that you're already used to.
Yeah, exactly. So that's for the designer. They feel like they're at home within MPLab. So you mentioned data. I think we need to count in machine learning, discussion how many times we say data. But that's really the key element here. A quick question is, how do we? So we say that we want them to collect their own data because it's not part of recognizing a cat from a dog. That's kind of a different business. How do we help them doing that? It's really to get the data, but how do they know that the data they have are correct?
That is the big question in machine learning, naturally. We try to help a little bit with the tools that we provide. So the reason why I think the data is important is I get a bit tired of machine learning tutorials where the first step is import this data, to press this button, now you have a machine learning model, and then it doesn't work. And that's because, well, data is hyper-local. And the data for my specific use case, and something that generalizes well, is completely different from what you have. And I think it allows you to build very valuable IP if you have your own data sets there. And I think that's where there's a bunch of companies that we work that really understand that and have started early on and say, well, we really feel that with the data that we're collecting, that could be valuable IP in the end. So we try to help a little bit. So as said, with MPLab, we allow you to stream data from your development kits and any device that can talk the serial protocol to MPLab. We have a couple of other ways in Edge Impulse. So we have our own ingestion endpoints. So if you have a device that speaks IP, and you can obviously get data off from that sensor, we allow you to just post that data directly to us. Then we have some data organization tools. So we try to find samples in your data set that are not contributing to the final outcome of your model. So one of the problems that we've seen, even in kind of data sets that are typically considered kind of state-of-the-art data sets that are used for lots of ML use cases, including, for example, Google's keyword data set, is that there are samples in there that are not correct, that are mostly noise, for example. So the Feature Explorer, which we have in Edge Impulse, is a quick way of identifying those types of kind of anomalous samples in your data set. So the approach that we take here is make it really easy to get data in, make it easy to manipulate data. So if you need to do auto segmenting on your data, like there's an interesting event that you're looking for, we can automatically do that for incoming data streams, and then visualize every step along the way. So machine learning should not be a black box. It's engineering. We should treat it as engineering. Getting your data set is also part of engineering, and machine learning is, in the end, the advice that I would give you is if you manage to solve a problem without involving any machine learning at any point, so after you've done your FFTs and your DSPs, you realize, okay, I can do this without machine learning, great, go forward with that. It's going to make your life a lot easier. Only if you can't do that, then go look deep in the data. We have got some nice tools for that. Alex will show you during the demo.
Yeah, okay. Yeah, so it's really to make machine learning for embedded designer, not for data scientists. Again, it's really to get, you're at home with MPLab, you have an easy way to collect data and make sure that the data you have are correct, and you can train and then you can deploy.
Yeah, I mean, but I do have to say, right, like, I think the 101 flow has been solved really nicely with this combination of Microchip and Edge Impulse. But going to like verifying this and deploying this on really expensive machines or deploying this in healthcare, it is still real engineering, right? I'm very confident that after you've watched today's webinar, you can get the little dev kit, you can take MPLab, you can take Edge Impulse, you can build something that works, and it works reasonably well within an hour or within 2 hours. That's great. But before you actually deploy this to real devices, that there is significant engineering effort still involved. So with one of our customers, we did a total data collection trajectory that took 6 months, and that gathered 4 terabytes of labeled sensor data before we were confident enough that this would actually work. So
that would depend on the
don't get the
on the application and what you're trying to do. I think we have some example of application here that we are showing. Maybe you want to say few words on those, Jan?
Yeah, so this, I would say this is a bit of inspiration. Like, so when we launched back in January at the Things conference, it's the largest LPWAN conference in the world out of Amsterdam. We figured we wanted to do something really cool, and we built something similar to what Alex has been building for an LPWAN powered activity tracker. And we got someone we got the CTO of the Things network in a sheep costume wearing that sensor, which was absolutely beautiful, and it was live classifying. So from that conference, someone saw the video, and he replied on Twitter saying, Benjamin Cabé, and he said, when I saw this demo, I was completely convinced this was staged. I didn't think this was possible. And right thereafter, he took his Seed Studio Wio terminal, which has a SAMD51, I think, in it.
Yep.
And he hooked up a gas sensor, and then he built his own his alcohol sniffing IoT device with Edge Impulse, which actually worked. Like it identified the correct alcohol between whiskey, brandy, and I don't know what else it was, as scotch or rum and scotch, with 93% accuracy in a absolutely brilliant little demo. So the stuff that we provide around vibration and audio and images isn't a good indication, but there's so much more stuff that you can do with machine learning that think a little bit outside of the box. So if you get one of the kits or you win one of the kits, I definitely want to see something like this on Twitter.
Yep.
And on useful things, what we participate with Microchip in is Elephant Edge, and there we help real wildlife in Africa, together with smart parks, in tracking where elephants are and if there's poachers in the same area. And one of the ways we do that is with collars that detect where the elephants are, and some behavioral science on that based on accelerometer data. But another project we're doing in the same region is to do with image sensors, or with thermal cameras that are powered by a solar panel. They run a small model, and when they see movement, they snap a photo, they run inferencing on it, and when they see a human walking around in a place where normally only elephants are, that is an indication that there might be a poacher around. So then, over satellite, a signal is being sent. If we see elephants in a place where elephants shouldn't be, maybe a herd is migrating, that's also when we send a signal. And the cool part is now you can build these things actually solar powered with a satellite backhaul. And that's it. And that's fantastic. You can have very little data. The only thing you need to send over is satellite communication is really expensive. The only thing we need to do is one is elephant seen where elephant shouldn't be, and 2 is poacher seen where poacher shouldn't be, and alert rangers that way. And you never have to change the battery again, which I think is super powerful.
Yeah, that's a very nice one. So while Alex is getting warmed up for his demo, one last question for you, Yann. What's the business model for Edge Impulse?
That's a good question. So for Edge Impulse, so I come from a long background of open source software and a long background of building developer community. And we started Edge Impulse because I was at ARM and I had my own team, and we were building machine learning software that could run fast on MCUs. And even though we had all of that, no one actually built a model from scratch. The farthest we got is we have a pre-trained model, we convert it, and now it runs on an MCU. So Edge Impulse really came from that thing. So for us, the developer community is super important. So we're free for developers. You can just go to the website, sign up, use 95% of the tools that we provide. Our compute is sponsored by our silicon partners, which is great. And the code that you output is always royalty-free and open source. So there's no compiled binaries. We'll literally just give you the exact source with all optimizations and all DSP and neural network code for that. Naturally, we do need to make money. So we have an enterprise version of Edge Impulse, and that contains, like I said, like the company that spent 6 months of time collecting data for their sensor model. We have really nice tools to do data collection in that scale. We have team collaboration that way, and the ability to plug in custom blocks. So Alex will show you our spectral analysis blocks to extract feature information from the signal on the dev kit. If your company is building, I think it's a nice way for your company, if you already have DSP codes that you have, you want to integrate that. We have really nice ways of sharing that with the rest of the organization and making that knowledge available in the company. So that's where our enterprise version kicks in. But definitely completely free to get started and completely free to get your code out, and no royalty nor license required.
And how do you get started? You go on your website on edgeimpulse.com, or how do you do that?
Yeah, so if you don't win a dev kit, you don't have anything laying around, just go to the website. There's a QR code. You scan it with your phone. And as we all know, phones are amazing little sensors. It has cameras, it has vibration sensors, and it has a microphone. So we allow you to build models with those 3 sensors straight from your phone to do the data collection. And afterwards, if you've done the data collection and you're completely convinced that this is definitely what you want to build, go order one of the dev kits. The source code that you can output will run here as is. And if you have a Microchip dev kit, you can just use MPLab to do data collection and send that straight away to Edge Impulse. So just go to edgeimpulse.com, scan the QR code, or sign up.
Perfect. So demo time, Alex.
Sure. Yeah, let's get started. So I'm going to show you how you can make a smart dumbbell with the SAM-D21 ML kit and the Edge Impulse Studio. So I'll start with the MPLab integration to show you how we can build a data set using our data collection tools. We're using MPLab Data Visualizer here, which is a plugin to MPLab. It can be downloaded within the plugins manager within MPLab X. And we're also going to use the machine learning plugin, which is a separate plugin that's also available in the plugins manager. So you can see here in the graph, I have the 6-axis of accelerometer and gyroscope data plotted. And so any data that I can collect here in the graph, I can then upload to the studio. So I want to train my model to recognize a few different types of exercises. So I need to give it some sample data to train the model. So we're doing a bicep curl here. And once we select the region by clicking Mark Window, then we can move over to the machine learning plugin where we can upload this data to the studio. So we select our data sources first. I have all 6 axes of the accelerometer gyroscope selected, and then my Smart Bell project within the Edge Impulse Studio. And we're going to send this to the training data set. I've given it a label, bicep curl. And now that we've uploaded, we can see the live upload here, and we can see the graph. And so this is my whole data set here. I have 3 different types of exercises, about 5 or 6 minutes of each. We have bicep curl, lateral raise, and overhead press. And within the data collection area, we can also create a test data set. So training data is used to train the model, and then the test data is used to verify its performance afterwards. So it's nice to have a little bit of each. Once we have our data set built, though, we can move on to the impulse design. And in this step, we can configure the input data, our DSP blocks, our learning blocks, and then the output features. So in the time series data on the left, we can configure the window size. For the data samples that we upload, that we just saw before, we can have any length of data sample uploaded, but for the actual ML classifier, we're going to need to trim those into windows that are meaningful length. So for recognizing periodic movements with a dumbbell, we need about a 2-second window to make sure we get a full cycle of the exercise so that we can properly classify. But then with the spectral analysis block is the DSP block we're using here in this example, and this is just a pre-built DSP block available from Edge Impulse that's really good with accelerometer data. And then we're going to use a neural network classifier to actually predict which type of exercise is being performed. And then we'll also use an anomaly detection layer to reject any anomalous data so that we don't get a false reading. And within the output features, we see the 3 classes as well as the anomaly output. So moving on to configuring our spectral features block, this is where we can configure the scaling of our data as well as apply a low pass or a high pass filter and then do a spectral power density analysis. And the cool thing about this interface here is we can see our full data sample up at the top, and we can select different regions to see how the DSP is processing the data in these different windows here. And then we can also adjust the parameters. Say if I apply a high pass filter, then we'll see my data gets a lot noisier here. And since I'm doing a low frequency periodic signal with exercises, I'm applying the low pass filter to just clean up the data a little bit. After you've configured all these parameters, you can move on to generating your features. And the features have already been generated for this example, so I'll just show you the Feature Explorer. And this is a nice tool we saw on the slide earlier where you can view the separation of your different classes of data, and if they're well grouped in different areas, then that's a good sign that your data will be well classified by the neural network. And you can also compare any 3 features generated by the DSP block here and graph them in the Feature Explorer. So moving on to training our neural network. Here we can configure the network parameters as well as the network architecture. And the input layer to your network is always going to be determined by the DSP block. How many features do you have coming out of your DSP layer? And then you can configure the size and number of layers for the hidden layers in your network. And for this example, since the DSP layer does such a good job at cleaning up the data, we only need 2 layers of 6 and 3 neurons each. And then the output layer is the 3 features are 3 different types of exercises. And so once the model training has been completed, we can see the performance here down at the bottom. So we can look at the accuracy and the loss, which are really important just to see how well and correct it's performing. But we can also look at the quantization. So if we use an unoptimized float, the performance goes up to 100%. But since we're only losing 0.1% here, then we're doing well with quantized 8-bit values in the neural net. After training your neural network, we can move on to training the anomaly detection layer. And here we're using a k-means clustering algorithm, so you can adjust the number of clusters needed to approximate your data region. And you can also adjust the threshold for trusting your anomaly layer. And then select which features from the DSP block you would like to use as input to this learning block. So I've selected just the favorites that are recommended by Edge Impulse Studio when you're using a spectral analysis block. It's just the RMS values of all 6 axes. And same as the Feature Explorer, we can explore the different features that we have from the anomaly detection layer to see where our data might fall. So if you want to test this, you can upload some anomalous data to your test set. And that's what I have here. And then we can visualize where this data actually falls within our graph. And luckily, it's mostly falling outside of the clustered region. And I think if we were able to compare all these axes at the same time, then we would see a clear definition between the normal and abnormal data. And so it's that simple, just to train your 3 layers. And once you have everything trained, you can move on to live classification. And this is where we have some nice support from MPLab X. If we just want to test a new sample of data that the model hasn't seen before, we can perform another exercise. I'll do the lateral raise here, a few repetitions. And once we fill this window here, we can mark it and upload it for testing. And then we'll move back to the ML plugin, and then I just change my data endpoint to testing, and we upload the data. And if we already have the live classification tab open, then it will automatically display the results. Oh, I put the wrong label on my data, if you noticed that. So I said bicep curl, but I performed lateral raise. And luckily, all 34 samples that were sliced out of this uploaded data were classified correctly. So you're able to see the sliding window here, just like we saw in the DSP block. And then you can also see a detailed output of each window that was sliced out of there, and we can see the readings from all different layers. So we have a confidence rating for each of the 3 types of exercises, and we also have a confidence rating from the anomaly detection layer. And another nice feature is within this Feature Explorer, when we're in their testing phase, we can see the data that we just uploaded is highlighted in red, and whichever actual sample that we have selected here will be highlighted with a larger blue dot. And so this helps just for analyzing if you have some performance troubles, then you can see where does this data lie in the actual feature space. And the same is available for the Anomaly Explorer like we saw before. And so it's that quick. As soon as you have some good performance that you like and the live classification, then you can move on to deploying your impulse. And in this step, you want to select the C++ library. This will just give you an open source library that you can add to your MPLAB-X project. And we have the Eon compiler enabled, which decreases our memory usage, and we're using the quantized 8-bit values for the neural net. And you just build here, and you can download a zip with all of the necessary source code. And so I'm going to move back to my project here and go ahead and program the device because I've already downloaded this code and added to my project. So the Edge Impulse Inferencing SDK is an open source C++ library. It uses TensorFlow Lite for the neural network calculations, and it has all the DSP block included, and you can also use the CMSIS accelerators if you're on the ARM platform to decrease the latency for the DSP and the neural network calculations. So we're going to connect on the terminal here because the inferencing firmware is going to output the results over UART as soon as it's done programming here. It's almost done loading. There we go. Okay, so it's going to continuously fill the buffer here in 2-second windows, and then as soon as the buffer's full, it will make a prediction. So you can see here as I perform lateral arrays, all this prediction is happening on the MCU with the DSP layer and everything. And we can try overhead press, another one that it knows. Whenever the data is not framed correctly in the window, then we see an uncertain or an anomaly. And we've also trained the anomaly detection layer in this example to detect if you're not performing the exercise correctly. So say I start doing a different variation of bicep curl that the model is not trained to recognize. Here we can see we're getting anomaly. But if we do the regular one, then it's working again. So you can't cheat on your exercises, and it's only going to provide the verification if you perform it correctly.
You have to do it correctly, and you have to do it,
Yep.
10 times. If you said 10, you cannot do, you just 8 and said I did 10.
Yep.
Good. Thanks, Alex.
Yeah, sure.
So before we, close here, maybe some question from Mike at the booth.
Yes, there are a good number of questions. We'll roll some of them into one question, or because they're very similar. So probably the most asked thing from, let's see, it's from Rushi, Caesar, Kevin, and Jared. They're basically asking what microcontrollers from Microchip can this run on? And can it run on, say, 16-bit DSPs, 8-bit microcontrollers, the MIPS core as well, or is it just ARM?
So today it's, and I let Yann also answer that, but today we're supporting ARM core.
Yeah, so there's fundamentally, so DSPs are a little bit different, but as long as it's a 32-bit processor, this will compile. It might just run a bit slower, so we can use vector extensions, for example, on Cortex-M to make this a little bit faster. But if we don't have that, we always fall back to software. So it does contain floating point math, so that might make it even slower on less capable MCUs. We use floating point math for the DSP code, but we always have a software fallback. So my principle here is always it should compile on anything. What is going to run fast, that depends a little bit. We do have, however, so if it's something you're interested in, like commercially, we do have are pipelines, but specific ones working on 16-bit DSPs. So if that's something you're interested in, just let me know, and we can have a chat about that.
Yeah, I think it would be interesting also from the different person who asked the question is what do we have in mind in terms of application, because as we discussed earlier, if you cannot do video recognition in 8-bit, obviously, but that's where we need to find the right the right applications. Mike?
Yep. So there's another question. Do they have the option just to pull in the DSP block?
That's yeah. I mean, in essence, so all the source code that we have is on GitHub as well. Do you have to go to only do the DSP block? Yes, just do just add an anomaly detection block, just select the single axis, and then don't use the anomaly. Don't use the anomaly results. So you can always pull out just the DSP results at any time. As said, it's just source code. So you just get the optimized DSP code plus all the parameters that you've picked, and you can pull it out at any time. So it's not completely made for that, but it's relatively easy to do that.
Interesting question.
So, yep. And also from apologize for my pronunciation. I think it's Arijit. He's asking about support. So where does he go to get support when he's working on a project? And I believe he's already working on one.
So at least on the Edge Impulse side, we provide support through our forums. So it's community support. So we have an FAE in US and we have an FAE in France. And if you look at the forum, you'll see that I'm also very active there. So we try to do our best, but but it remains community support. We have commercial support as part of our larger offering. And for Microchip, I'll defer it to Jan.
Yeah, for Microchip, so we can help you obviously on the getting the data, from the plugin and MPLab like Alex just showed. We can help you on the integration as well. We also have a team of FAEs that who are more knowledgeable on machine learning, who can maybe also help you and guide you on are the data correct, which kind of model you should use, and things like that. And then we can work in coordination with Edge Impulse to get you the best answer.
And we have another one from Jared. I believe it was answered, but it's probably good to repeat it. Does this use a prominent open source library on the back end, such as TensorFlow? And the UI ease of use looks amazing. TensorFlow seems to require the engineer to do almost everything from scratch.
Yeah.
Very good point.
Yeah, so we use a couple of we use part of TensorFlow. So I think one of the things that the guys at TensorFlow have been doing is very well is kind of build this amazing community around the product where virtually everyone is targeting TensorFlow Lite for microcontrollers first when they're porting performance work, for example, somewhere. So for general purpose MCUs, it's a little bit different on like DSPs and things with a neural network accelerator, but on general purpose MCUs, we typically use the TensorFlow Lite kernels, but with Eon, which is our own neural network compiler. And what Eon does is kind of a nifty little trick. So the problem with TensorFlow Lite, one of the issues with TensorFlow Lite for microcontrollers is that it has this interpreter, and then you feed a flat buffer file in, and then internally in your MCU you rebuild kind of the structure of the tree or of the model, and then you invoke that. And that's very wasteful. So what we do with Eon is we load your model somewhere in our server in the TensorFlow Lite runtime. Then we serialize that graph back to source code, and then we just let you compile that. And so everything that is not required will automatically be linked out, and that yields 35 to 50% RAM savings and about 30% ROM savings on typical models. But naturally still using the same kernels because, well, that is really fast. So we do that on ARM cores and on a few others that I won't mention in this webinar. But yeah, definitely.
And we have another one from Eric. Because X, Y, and Z are totally arbitrary, how does the orientation of the sensor during training and testing get baked out? Is there an up-down normalization step that happens somewhere?
For my example, there's no normalization, so I collected data from all orientations of the dumbbell, and the model does well to classify no matter what orientation you use. So the machine learning and the DSP are able to solve that problem for you.
Yeah, but it's a data issue, right? You can't just generalize and say the orientation doesn't matter. Maybe it does for you. Well, maybe it does for your dumbbell, maybe it doesn't. Like Alex was doing this movement, which was incorrect, and this movement was correct, right? In this case, the orientation actually matters. So really think about your data and then capture variations of the data, or make synthetic data from the things that you have. But I don't think you can generalize it that well.
So, and yeah, I believe that's the last of the questions. So everyone, remember, fill in the survey. You get a chance to win this. And if you do have more questions or I accidentally missed them, please send an email to livestream@microchip.com.
Thanks, Mike. So I think it's time to say goodbye. I hope you enjoyed the discussion we had with Alex and Yann from Edge Impulse here. And I say, if you have any questions, just drop it in the chat or send us an email, and we'll get back to you. Thank you for joining. Bye.